Going to talk about log transformation, understand what we're doing when we log transform. Okay. So what can we do when we don't meet the assumptions? If sample size is large, we know maybe we can ignore it. However, when we want to use something like a t-test, parametric distribution-based statistical test that has the greatest power to detect a difference if there is one, and we don't meet those assumptions of normality and HOV if we're talking about a two-sample t-test, we'll try transformation before we go on to something like a non-parametric. So transformations are a mathematical function, okay? So we're talking about doing this natural log. It changes the scaling of the data. It changes the magnitude of the range so that the relative spacing between them usually shrinks, okay? So we're talking about log transformation. There are others like squaring or doing the inverse. We're not going to focus on those here, but you should know that they're out there. So we've seen over here, especially with right skewed data, that log transformation can really help them look normal, and you can see that the tail is what's being normalized, or well, maybe normalized isn't the word, but brought down the scaling from this smaller to all the way to this larger. And log transformation is always really especially helpful when one of the groups has a larger mean and a larger standard deviation than the other group has a smaller mean and a smaller standard deviation. And that tends to not only fix the normality problem, but also the HOV. Quick review of exponents as we've seen, and we'll see that this is the one that we're especially going to be focused on in terms of what happens in our log transformation and what that means for interpretation. Quick review of logs. They are exponents. So we've log base 10, which you've probably seen before. Log of 10 is 100 equals 2. So just means that raising the base 10 to the 2 equals 100. So natural log is the base E, 2.7183. And that's similar, though, in terms of the natural log 30 equals 3.4012, because if we needed to raise the base E to 3.4012, that would equal 30. All right, here are the basic steps. You know that you violated normality and or HOV. You specifically test for that using the Anderson-Darling and Levine's test. You can't ignore it. So you go in and you log transform every data point. Okay, so it's very simple. We'll practice this in class. Then you find the mean and standard deviation of the log transform data. You'll look at your histograms again. Go ahead and recheck those assumptions, normality and HOV, to make sure this fixes the problem, because you don't want to end up having a different problem. So you got to recheck. Then you'll run your statistical test, say a two-sample t-test. And then you'll need to, in order to interpret the means of the groups and the confidence intervals, either for the difference or for each group, we have to back transform these values. Now, in this case, we don't back transform every value and then get that mean. No, we'd be back to where we started from. What we do is we only back transform the mean. And so that's just taking the log transform mean, back transforming that. For confidence intervals, you get those upper and lower limits that are given out in Minitab or Excel, but generally Minitab for us. And you back transform just those upper and lower limits. And that will let you interpret your results. Okay, and this is why, okay? So on a log scale, adding numbers is the same as multiplying the original data, or subtracting is dividing. So we're going to see this relationship become important when we're talking about how this changes our null and our interpretation, mathematically how it changes our interpretation of the null. And this relationship, which is really important because this is taking, back transforming that mean. And so when we do this, it's the same as taking the n root of the product, and that becomes the geometric mean. So when we back transform the mean of log transform data, we no longer have the arithmetic mean, we have the geometric mean. It's another measure of central tendency, and it's actually closer to the median and mode. It's better than the arithmetic mean for a central tendency than uh, the geometric mean is better than the arithmetic mean when we have highly skewed data. And that's because it doesn't get pushed by those outliers like the arithmetic mean does. Remember those shiny outliers? Okay, and when we're comparing two log transform means, and this is the interpretation difference, the difference in the mean of log transform data is really the ratio. So this ratio, difference in log of means, is what we end up actually testing for in our null. So our original null in a 2 sample is the mean of the group X minus the mean of the group Y equals 0. After we have log transformed, because of this relationship turning these into exponents, we now are actually testing a null of the mean of X over the mean of Y, the ratio, and does that equal 1? Okay, so that's what we're testing now after log transformation. And as I said, back transform the upper and lower limits of any confidence intervals you're looking at. You don't want to back transform the standard error and then calculate. That would be wrong, because what happens, you need to just use these upper and lower limits, because this confidence interval won't be symmetrical. And that's also true because of the skew in the original data. So it's changing our analysis a bit. The math is pretty straightforward. It just makes it a little more complicated. We're not going to talk about these other transformation techniques, but you know, it's a little more complicated, but not too bad. And here's a nice visual for us where we see the geometric mean is staying where the bulk of the data is, not getting pushed out like the arithmetic mean would. That's why it's a better measure of central tendency and skewed data. And then we can see the 95% confidence interval around this geometric mean, okay, is no longer symmetrical because it's representative of that skew in the data. Okay, so this 95% confidence interval is around the geometric mean, not the arithmetic mean.